Just one small correction. A lot of what I have to say is directed to students and their faculty mentors. Because one of the points I'm going to make, and it will pervade this talk, is that to take innovation out of the scientific laboratories into the clinic requires starting companies, and faculty members who start companies are key to the entire process. I just want to give you a little bit of my own background in biotechnology. It actually started when I was an undergraduate at Kenyon College, spending a summer in a chemistry lab at Stanford University. You may not recognize the name Carl Djerassi or Syntex SA, but I am reasonably confident that about half of you have used the drugs that they make. Carl was, he just passed away, a leading organic chemist, particularly in steroid metabolism and chemistry. He is known as the chemical father of the oral contraceptive pill. And the company he developed, Syntex SA, made a fortune in oral contraceptives and also really changed enormous social and political and everything else in the world as a result. I mean, basically freed up people. Let's leave it at that. But you see the point. When I was in his lab, he was training graduate students to do some of these chemical reactions. As soon as they worked, he shipped them over to Syntex. The point is that scientists were starting companies. He retired as a billionaire. Do you know how much money $1 billion is? It's 1,000 million, okay? I'm going to use that number extensively. But he became a billionaire and actually formed an artist colony. So chemists, business people were involved, academics, in business for a long time. Beginning in the late 70s with the recombinant DNA revolution, a number of academic scientists, myself included, got heavily involved in starting and nurturing biotech companies. The two that I helped found, Genzyme, and I'll talk about some of Genzyme's products, that was sold fairly recently for $20 billion. Millennium, which makes, among other things, the proteasome inhibitor for multiple myeloma, that was sold to Takeda for $15 billion. And I've still been starting companies, and I'll talk a little bit about Rubius, which just got off the ground last summer. In addition to that, I've worked very closely with the former governor of Massachusetts, Deval Patrick, and he asked me to head up the advisory board for this $1 billion, $100 million a year initiative to support life sciences in Massachusetts. And when I say support life sciences, this is under the aegis of the Secretary of Economic Development. And it's basically to develop life science companies in Massachusetts, both to increase jobs and local economic prosperity, but also to create new drugs and medical devices. And the high-level conclusion that I want to leave you with, and I'm going to go into many of these details, that is, academic labs do the basic science, the infrastructure for developing molecules that might become therapeutics. But in no way can an academic lab actually manufacture and clinically test a drug. For that, you must have a company that can make the molecule, whether it's a small molecule or a protein, manufacture it under good manufacturing practice, package the molecule, make sure it's stable, make sure it doesn't have any of 100 side effects, conduct the clinical tests, and actually market it. So what we're talking about is an intense multi-level collaboration between academic labs, both in universities and in medical centers, together with government-supported research, not only research but government-supported development. As you'll see, patient-based organizations are increasingly becoming critical in developing drugs for fairly rare diseases. And I'll give you some examples. Philanthropic support, but particularly small and medium-sized biotech companies. That is, one of the paradigms that has emerged is that large companies cannot do innovative research. They simply don't know how to do it. All of the innovation in life sciences, pharmacokinetics, and machines comes out of innovative small companies that are generally started by faculty members. Okay? The multinationals will handle the manufacturing and the marketing, but they cannot do the innovation. They won't tell you that, but that's the fact. And I'll explain towards the end how this plays out in Boston. So what I'd like to do is go through two examples from my own experience. Genzyme, particularly the drug for Gaucher disease, and the new red cell company that is just off the ground but is already well financed. I'll give you several examples of companies that I don't work with but know very well that have developed highly innovative technologies based on an understanding of molecular and cellular biology of the disease that are leading the way to new therapies. And then I'll end with some general lessons I've learned as to how to start and nurture small companies, and a little bit, depending on the time, of what the Boston-Cambridge life sciences community looks like. And we'll see where we go. So let me start with Genzyme. So we started the company. There were 8 of us, including chemical engineers, biochemists, geneticists, microbiologists, and so forth. The first 2 major products, one was the enzyme replacement for Gaucher disease that I'll talk about. The second is hyaluronic acid, which in itself is an interesting story. That is, hyaluronic acid is a natural product. It's found in joints. It's part of, it tethers various proteins, collagens, and so forth. But basically, it's a lubricant. It's a very hygroscopic molecule. Now, it finds many uses, as I'll go into, but it could not be made. The only source of hyaluronic acid that could be at all used medically was rooster combs. Okay? Now, the supply of roosters is not so great, and it's not a good source for a pharmaceutical. It was known that many bacteria made hyaluronic acid, but the hyaluronic acid was too small. The polymers were only a few hundred in length, and they didn't have the right viscoelastic properties. But very quickly, one of the founders, colleagues who founded Genzyme, Graham Walker, a world-class microbiologist, realized that the bacteria were probably making the long polymer and then degrading it with hyaluronidase. So he persuaded one of his postdocs to move over to this tiny company called Genzyme and isolate bacterial mutants that were defective in hyaluronidase. That was not difficult to do once you thought the process through. These bacteria made high molecular weight hyaluronic acid, which is now marketed as several forms. Basically injectables for knee osteoarthritis, cataract surgeries, sheets of hyaluronic acid which are used in abdominal surgery, and so forth. So just a simple example of how biological insight can create a product. Many of you might have used it in lotions. Most of the moisturizing lotions have this wonderful hygroscopic property because they contain hyaluronic acid. Now, what Genzyme is most noted for is Gaucher disease. This is an inherited autosomal recessive lysosome storage disease that can become progressive and debilitating. A lot of symptoms that are often very difficult to diagnose without genetics, particularly anemia, because the bone marrow fills up with macrophages that can't degrade this glucocerebroside, but basically bone and joint pain, huge enlargement of the spleen and liver, again filled up with defective macrophages and so forth. And it's the most common lysosomal storage disease. As I said, it's defective in an enzyme called glucocerebrosidase, which is necessary for degrading this ceramide, glucosyl ceramide. And basically, it's this molecule that accumulates in the macrophages. This is a normal glycolipid, but macrophages, of course, degrade outworn, aged cells, and this lipid simply accumulates in them. Now, for reasons that we'll come to in a moment, just bear with me. I need to give you some additional background information on Gaucher disease. So just bear with me. Depending on how much residual enzyme is left after the mutations, the most common type, type 1, which is common in Ashkenazic Jews, basically has enough residual enzymes so there's no defect in the brain. And it's the one that has all the symptoms I just described. But if the mutations are such that there's little or no residual enzyme, under a few percent, you can have severe brain developmental problems, either early death or mental issues or both. Okay? So just bear with me for a moment. But basically, the treatment that was developed was for the type 1 disease, the Ashkenazic, which is common in Ashkenazic Jews. And it's an enzyme replacement therapy, but you simply cannot inject the enzyme into people. It'll circulate in the blood, it gets degraded, and there's no degradation of glucocerebroside. You actually have to modify the enzyme in ways that I will describe, such that when you inject it, it's taken up by the macrophages, by receptor-mediated endocytosis, internalized, and it goes to lysosomes. Okay? That was the cell biological problem that had to be solved. Okay? You see where I come from. So how is this done? Well, you piggyback on a receptor in macrophages called the macrophage mannose receptor, which is part of the innate immune system. That is, many foreign pathogens, particularly fungi, have on their surface polymannans. Here's an example of a yeast polymannan. You can see all the M's, which are branched mannose chains. This type of carbohydrate never exists in the human body. We just never have the enzymes to make it, fortunately. So basically, the receptor on macrophages, as part of recognizing fungi, binds to this mannan. And here you can see examples of macrophages that are ingesting a yeast particle via the macrophage mannose receptor, which was discovered and characterized by Phil Stahl at Washington University. Okay? So basically what was done, it was actually first done at NIH in, I'm terrible at names, but I know them very well, so you'll have to forgive me. But they developed the original methodology at NIH, and basically Genzyme made the molecules. But what was done is you make the recombinant protein that is secreted from cells. And although many of you don't care a bit about carbohydrate metabolism, it's actually a very important piece of cell biology. And the point is, the normal proteins that are secreted from cells will have the common 3-mannose 2-N-acetylglucosamine core that is found in all N-linked oligosaccharides, but outer branches of sialic acid, galactose, and N-acetylglucosamine. And the product that Genzyme makes now in cells is the recombinant protein in which successively the sialic acid, the galactose, and the N-acetylglucosamine are removed from the purified protein by enzymes, leaving behind this core of 3 mannose residues, which is a lovely substrate for the macrophage mannose receptor. And this then provides the way in which the recombinant protein is taken up by macrophages. So you can see the impact of cell biology on this drug, which is, it's an expensive drug, but it works. So this is one of the first disruptive technologies that I want to describe for you. First of all, it was one of the first recombinant protein drugs, developed about the same time as erythropoietin and GCSF and a few others. It was a personalized medicine for a rare disease, and increasingly we're seeing more and more of them. And it is also based on glycoengineering. Okay? So that's the Genzyme story. But there's more to it. Why am I showing you this picture of my 3 children, their spouses, and my 7 grandchildren, taken in Belize about a year ago in front of Zanatunic, a Mayan ruin? Why am I showing you this picture? And why is this young man, Andrew, on the cover of the Whitehead Scientific Magazine? Okay, the point here, and it's a very important one, is that when his mother, who's our daughter, was pregnant, she was offered this test of genetic diseases. She and her husband, both of Ashkenazic Jewish heritage, were offered this battery of tests. Pardon me, it's the Jewish panel. It turned out that she and her husband were carriers. She had no idea that I knew anything about the subject and went ahead and had amniocentesis and found out that the child she was carrying had Gaucher. But we could tell from the genetic testing that he was going to have the mild case treated with Grandpa's drug. Okay? And furthermore, the physician at Boston Children's who was treating him, Ellis Neufeld, Ellis I knew since he was a child because his mother, Elizabeth Neufeld, is world famous for discovering really the molecular and biochemical basis of lysosome storage diseases. So the article, and it's publicly available, here he is actually getting Grandpa's drug. And, you know, he's a perfectly normal kid. Actually not. He's above average. But you get the point. Okay? So, and the point here is a very important one. That is, we're in the business of making money and developing companies and creating jobs and all that. But there are an awful lot of diseases we cannot cure. And the objective now is to develop therapies, and I'll give you many examples going forward, of drugs that treat diseases that we can no longer cure or cannot cure. And the obvious point is you never know who's going to benefit from the drugs that you develop. I had no idea it was going to be my grandson. You have a question? Yeah, good.
Disruptive drugs. What is disruptive?
Because this, you'll see, new technologies that go beyond what exists now. For instance, I'm going to talk about gene therapy. Right now, he has to go every other week to the hospital to get an infusion. That costs about $200,000 a year. It's covered by insurance. And I'll show you some of the papers. I am convinced in 6 years, when he's 18 and of legal age, he will make the decision, it will be his decision, to go to Boston Children's Hospital and have gene therapy performed, and he will be cured for life. That is a disruptive technology. Okay? And I'm going to show you many others. That's what we're talking about. This was disruptive 35 years ago. No one believed you could either do it or build a company on personalized medicine. Okay? So let me go on. what's this company? Okay, now, many of you, not all of you, have heard the previous lectures I gave on red cell development. And basically, we have been working on making red cells in culture, both mouse and human red cells, for many years, basically to study the genes that are that are required to make a red cell. And one of the things we developed, and I went into this in more detail, let me go here, is a cell culture system in which we could take human bone marrow stem cells, mobilized stem cells, and grow them for 21 days in culture and make perfectly normal human red cells that actually survive when you inject them in immune-compromised mice. And we can add or delete genes at will. And I was giving a lecture on an extension of this subject at a systems biology meeting, and afterwards Nubar Afayan came up to me and said, Harvey, I think we have a company. Nubar is the founder and president of Flagship Ventures. And I knew him very well because I was on his thesis committee about 30 years ago in chemical engineering. You see how Boston works. And the idea was to use red cells, recombinant red cells, as a vehicle for introducing therapeutics into the human body that will live for the lifetime of a red cell, which is 120 days. And these are actually very attractive ways of introducing therapeutics. They have a long lifetime. We know a great deal about the genes, the proteins on a red cell. They have no DNA, so there's no danger of introducing oncogenes or anything else. You manipulate the nucleated cells, they lose their nucleus, and that's what you inject. Okay? This is a brand new company. But of course, blood transfusions are very common. So rather than saying you're getting a recombinant cell, you say you're getting a blood transfusion. Okay? Now, I can't tell you which product is going to work, but I and the investors in the company, and we're already up in the multi-millions of dollars, are convinced, as is DARPA, the Defense Advanced Research Projects Agency, which supports also some of this work in the States, that we can equip red cells with single-chain antibodies that will neutralize all manner of foreign pathogens and toxins. We can equip them with receptors that bind molecules such as lipoproteins or immune complexes and remove them from the blood. We can equip them with protein or other types of sensors. It becomes a very versatile platform. We use single-chain camelid antibodies made by alpacas. And for instance, we've already incorporated onto the surface of red blood cells these single-chain antibodies to botulinum toxin. And they protect against botulinum toxin. That's just a proof of principle. What exact product or products will make it to the market, I don't know. But I can tell you the company is thriving. The first employee was a young woman who worked in the lab of my collaborator Hitter Ploch at the Whitehead Institute, and she became the first employee of the company. And she got some stock. Okay, now right now the stock is worthless. But if any of these products develop, not only will we have a product, but several people will become quite wealthy, thank you. Okay, you see where we're going. We can put metabolic enzymes and all kinds of things. So I was asked about other innovative and disruptive technologies. Well, one we can start with is this one. Okay? Now, I read the Boston Globe, which is a very good local newspaper for biotechnology. And I see $100 million. I had no idea what this company is. Okay, but when they get $100 million with an option to acquire the company for $1 billion, I start reading. Okay? And it's a drug for myeloma. Now, just go slowly. Myeloma is a tumor of plasma cells that secrete high levels of antibodies, either light chains or immune complexes, and it's a tumor. So what is this drug? Well, anyway, I'll come to that. They have this drug. I mean, you can read it while I'm talking, but, you know, they put it in humans. It works. I had no idea what this drug was. So I'm curious. So I go into the website and I start reading papers. It's an inhibitor of histone deacetylase 6. Now, many of you are cell biology graduate students, right? Okay. Can anyone tell me why a HDAC6 inhibitor might be useful in the treatment of multiple myeloma? Let's come. What? What? No. What? What? Yeah?
I don't know, I can't remember if it
No, I'll give you a clue. It has nothing to do with histones. Aha! What? Who said that? You're a faculty member. You don't count. Okay, but let's just go through the history of it, and then I'll show you the key paper. Okay? This is real cell biology, guys. Okay? But you see where I'm coming from. So they developed this at Harvard. Okay? And then they go to the Dana-Farber, which is the cancer hospital, and they realize that this early stage inhibitor could be used to treat multiple myeloma. And then they go to high throughput screening labs at the Broad Institute and improve it, basically getting a more selective HDAC6 inhibitor that has low toxicity. And then in 2008, they formed the company. Now look who's in the company. Ken Nixon is the oncologist. Jay Bradford is the chemist. They're both Harvard professors. Okay. Ralph, I don't know. He's at the Broad Institute. And then there's a wealthy guy named Mark who heard about it while he was on the board of trustees of the Dana-Farber Cancer Center. And then they hired Walter, who becomes the president of the company. And they get $7 million for investors. And now it's very interesting. They get a lot of funding from the Leukemia and Lymphoma Foundation. This is a patient-based disease foundation, which puts a lot of money into academic research, but didn't get a cure for a lot of the blood cancers. So they supported the research in the company in return for a return on the royalties. It's a very interesting financial model. But basically, they went through human clinical trials. It works. Celgene gave them $100 million to develop it with an option to purchase the company for $1 billion. Okay, so what's going on? It is, in fact, inhibiting deacylation of microtubules. Now, again, multiple myeloma is overproduction of misfolded or incompletely assembled antibodies. There's a lot of ERAD, endoplasmic reticulum, export of misfolded proteins into the cytoplasm, a lot of proteasome-mediated proteolysis. That's why you can treat the disease with a proteasome inhibitor. That's what Millennium does. But it doesn't work that much. The other way of getting rid of misfolded proteins is you move them along microtubules to a collection point near the Golgi, where they just accumulate and, in principle, don't affect the cells. That process, acetylated tubulin is very stable. Unacetylated tubulin is relatively unstable. If you lock the microtubules into a stable state, you can prevent this movement of the misfolded proteins along the microtubules to the collection point, and therefore, if you double that with the stress of the cell and the proteasome inhibitor, you kill the cell. Okay? It works. So let me give you a couple other examples. Gene therapy. That is now becoming, it's at the academic stage. Here's a report from England on an AAV treatment of hemophilia B. This is factor 9. It's a magnificent paper. I read it with my students. A single injection of the recombinant AAV can produce enough factor 9 to last many months. Okay? Here's another one out of Boston Children's Hospital. A gamma retrovirus vector for X-linked SCID. Basically, they're treating very successfully severe combined immune deficiency, Wiskott-Aldrich, and eventually other therapies. Now, the clinical trials are done at Boston Children's. The vector is manufactured by Bluebird, and I'll come to Bluebird in a moment. That is a company established in Boston initially to use lentiviral vectors to treat thalassemia, another very difficult to treat hematologic disease. The point is, in order to do these clinical trials, you need a lot of these viruses. You can't make them in a research lab in the hospital. You must have a company. So then I go on, and then I see this the same Boston a few weeks ago. I said February 11th, Voyager is another AAV company. I'm not even sure what they do, but you see Sanofi, this is a startup company. Sanofi paid them close to $1 billion to work with the company, not to acquire it, but to work with the company. You see, the big companies can't do this. They have to work with the small companies. So I went on and read the article, and then I was stunned by this paragraph and read. It says, Spark Therapeutics, a Philadelphia gene therapy company, went public at a valuation of $1.2 billion. Now I said, holy smokes, because I know the president, that's Kathy High. Okay? She is a very respected hematologist. I knew she was working on AAV gene therapy, but I thought for factor 8 and factor 9. I said, what in the hell has she done that earns a $1 billion valuation of the company? Do you understand how much that is? You know, the gross national product of Israel is $300 billion a year. Okay, that's good. Every goods and services made in this country in a whole year is $300 billion. So $1 billion, let alone $20 billion, is a lot of money. Okay? So I started going in and talking to people, and what they do is cure the blind. Okay? You want a disruptive technology, here it is. These are hereditary blindness. Basically, a series of enzymes and proteins that are involved in the visual cycle. You take, remember, it's all cisretinol, it's 11 cisretinol, and it's photoisomerized to the transretinol. You all remember this, of course. And then in order to reisomerize it, it has to go out of the retinal cells into the retinal pigment epithelium, get isomerized, and shipped back. There's a whole lot of enzymes. If you're missing them, you go blind at a young age. Okay? They take kids and restore their sight. And the movies are extraordinary. Okay? That's what they're making money on. But it's not only making money. I mean, you know, I was actually moved when I read this, and I said, okay, look, I'm coming to the Holy Land, and here you go. Okay, this is Isaiah in the Old Testament. You know, he prophesied this, but it can now be done. And then I went into the New Testament, and when I found this, I jumped because I misread it. I said they came to Bethsaida, but I read it as they came to Bethesda. And I said, no, it can't be. But you see the point. I mean, there are many stories in the New Testament of Jesus curing the blind. Whether he actually did it or not is not the point. But for millennia, people have wanted to do it. And now with gene therapy, one may be able to cure a lot of these genetic forms of blindness. Okay? Here's another company that is even more disruptive and revolutionary. This has no products, but this is a Cas9 company. And you all know what Cas9 is, gene editing. You can imagine what you can do with it. But if you look at some of the advisory board members, this is a who's who in Cas9, including Jennifer Doudna, who really is credited with a colleague in discovering Cas9 as a mammalian genetic editing device. Now, they don't have any products at all, but it's clear that this is going to be a technology that is going to work. Okay, and you won't know any of these people. I know them, but these are premier business people with PhDs who work in the companies that are backing Editas. Okay? And then I just went into, in Massachusetts, a few of the top VC companies, venture capital founded companies. These are companies that got, this is millions of dollars, so 160 or so on. What is Moderna? Another disruptive technology. This is gene therapy using messenger RNA, no DNA. Okay, they use modified RNAs that are made synthetically modified to be taken up by cells, and you can use it for a whole variety of gene type therapies. And it works. And again, you look at the scientific advisory board. The head is Jack Shostak, who was a Nobel Prize. The point being that people on advisory boards of these companies are among the most respected scientists who advise and nurture and help develop these companies with the new technologies. Okay? Ken Chin, Bob Langer, some of you know, who has somewhere around 800 patents. Doug Melton, who wants to use this to cure diabetes, and on it goes. Betsy Nabel is head of one of the biggest research hospitals in Boston. She's on their board, and so forth. Here's another one I picked because of its cell biology. This is Karyopharm, which is developing inhibitors of nuclear exportins. These are the proteins that chaperone proteins out of the nucleus. And the first reaction is, why the hell would you make a company on this drug? Well, it turns out in a number of tumor cells, EXPO1 is overexpressed and exports from the nucleus certain tumor suppressors that would otherwise suppress oncogenicity. And they have indeed developed targets that look like they're working. And again, if you know some of these people, you'll know that they're among the tops in the field. Here's another one. This is cancer immunotherapy. I go into their website, it says absolutely nothing. But then I look at the company founders and I see Jim Allison, who basically discovered the antibodies against PD-1, which is the basis of a lot of the immune therapies based on unleashing T cells, with very promising clinical trials. And again, you can do all the work you want in an academic lab, but to actually get something into the clinic, you got to have a company. There are medical device companies. Let me skip over them. And let me go, what have I learned through all this? Okay? First of all, the point I made at the beginning. That is, academic collaborations are essential. No one group can do this alone. As I think you now understand, you need the collaboration between leading academic scientists, work that goes on in their labs, in our labs, clinical labs at medical centers, philanthropic support. Do you know the story of cystic fibrosis? Where the Cystic Fibrosis Foundation underwrote Vertex's development of these magnificent cystic fibrosis drugs. The CF Foundation put $700 million into development of these drugs in return for a royalty stream. They monetized, that is, sold the royalty stream to an investment bank for $3.6 billion. So the Cystic Fibrosis Foundation in the United States now is an endowment of $3 billion, an endowment to support research. Okay? from simply supporting development of a drug to cure the disease that affects the children of many of the people who gave the money. Okay? It's a win-win situation. Now, to start a biotech company, you need an entrepreneurial environment. You need an environment where academic scientists are encouraged and have role models to start and develop companies. You do not have that tradition in biology and in biotech in Israel, although you do in high tech. We have it in Boston. We have it at MIT. You need a top scientific advisory board. Often some of the people who either develop the technology that you want to exploit or who are leaders in the field that can nurture the company. You need protected intellectual property. You need a business plan. I'll go into this in more detail in a moment. You need venture capital. You need people who are smart, who are scientifically trained, who have the financial money to invest and nurture these companies. And you need a helpful government and regulatory affairs. So just going through it very quickly, in most of the successful startups that are going on in Boston, it's the top faculty who put the company together. It's often their students and postdocs who work in these companies. You need highly trained PhD people. You need lower level employees to actually do much of the lab work. You need people expert in business, law, finance. You need them all together in order to make this work. And just parenthetically, because there's a lot of misconceptions. If you look at the life sciences industry in Massachusetts, which I'll go into in a moment, only about 20% of the employees have PhD or MD degrees. Somewhere around half have either bachelor's or master's degrees. There are enormous career opportunities for motivated people at all stages of their career development. And that's very important for you guys to know. It's important for everybody to know. Again, a scientific advisory board, you have academic scientists, oftentimes retired executives, or even current employees of companies. You need to work together as a group. That's often not easy in academia. But this is part of what you have to do. You get stock in the company, which if the company is sold or goes public can be worth a great deal of money. And this is the group that basically recruits the presidents, the leaders of the company, the scientific leaders of the company, and also allows the company to move quickly into new directions if the research indicates. Okay? You need intellectual property. You need very good patent protection. You often need a superb university technology licensing office. I don't know what the situation is here. But you need people with business expertise and the scientific insight to be able to market university developments to some of these companies. And they need to be familiar with patent protection, licensing, royalty agreements. And I generally encourage anyone who's interested to get their own attorneys. I'm not joking, because a lot of money is at stake. You need a business plan. And this is probably the most foreign thing for academics to think about. You start a company for one reason. You don't start a company to develop a drug. You don't start a company to cure a disease. You start a company to make money. Because if you're going to attract investors, you're going to have to give them return on investments. You actually have to have a business plan as to how eventually you're going to make some money. And academics are not very good at that, at least not at the beginning. You can get to be good at it. You need to know what it's going to cost to do the research and development that you want to do. Who is going to buy it? What is the market size? How many patients are there with the disease? And how much are they going to pay for the drug? What is the competition? Are other companies making similar drugs? Are there related drugs on the market or not? What kind of intellectual property do you have? And what kind of intellectual property might others have that would block you from doing what you want to do? And what is your exit strategy? Are you going to become a full-service biotech company? Are you going to have an initial public stock offering? Or increasingly, your plan is to go into early-stage clinical trials and then sell yourself for a couple $100 million to a big company. But if you're going to get investors, you need to have a strategy as to how somebody's going to make money in the end. Okay, I hate to sound crass, but this is the reality of the world. Okay? You need venture capital. Now, most people think venture capital is supported by millionaires. It's not. It's pension funds, it's university endowments, it's all kinds of money that is invested in securities. And in most endowments, in most pension funds and so forth, somewhere around 5% of the money is invested in venture capital. That is high risk, high return investments. And these companies, many of them have become very skillful in identifying market opportunities. I described my own experience with flagship ventures. But basically, the founders usually identify the venture capital firm, and on the board of directors of the company, you put one or more members of the venture capital company. Oftentimes, as the case with my little company and most others, a venture partner will become the interim president, because that person has a scientific background, usually, but also understands business. How do you run a company? How do you hire people? How do you pay people? What's a payroll? All that stuff, okay? And then work with the scientific advisory board to generate a corporate board of directors, a permanent CEO, chief executive officer, and so forth. Now, I guess that's really the last in that series, but again, for very rare diseases, and increasingly I'm dealing as an advisor with many of these, companies don't work because no one will put in the money, and it basically depends on philanthropy. But don't get discouraged, because there's a move in the States. Some of you may have seen the article. In fact, I was interviewed in the Wall Street Journal in December on parents starting for-profit companies to develop drugs to cure their children. Okay? And increasingly, these become for-profit companies, but we have to be careful. So let me just give you an idea of what's going on in Boston. Okay, the first thing we have are incubators. Lots of them. These are basically rent a lab bench, rent a 50 square meter laboratory. Start your small company in a little lab, but in a center that has equipped with all the gene sequencing and cell sorting and microscopes and everything else that you need to run a first-rate biomedical research lab. In other words, you rent the bench and you rent the ability to use all of this equipment. The incubator often has people in it who are experienced in business and patent law and so on that can help nurture the company. And as I'll describe, my little company isn't such an incubator. It's called Lab Central. Okay? Mostly in eastern Massachusetts, we now have 500 biotech companies. And it's growing almost every week a new one is started. If any of you are interested in coming, because I do wear a hat of economic development, if any of you are interested in starting or developing a company in Boston, let me know. I can put you in touch instantly with the right authorities. You want them in Israel? Okay. Well, then you're going to have to follow what I said and set some of this up in Israel. What I'm actually encouraging, no, this is not a joke. Just this is not a joke. What I encourage I do this a lot in foreign countries. I say, start companies in Boston. Move some of your top scientists to Boston, set up and develop these companies, and then when they have more than 10 employees, move them back to your home country. But learn how it's done in Boston. That sounds arrogant, but it works. Okay? Okay? And there are many examples of this. I see you chattering among each other. Okay. Okay. We have 400 medical device companies. A lot of venture capital money. Okay? Now here's a map. Okay? This gives you an idea of the proximity. This arrow is the Whitehead Institute. These are various kinds of big pharmaceutical companies, little pharmaceutical companies, and this doesn't include the hundreds that are in the small incubators. But just to give you an idea, here's where I work. Here is the incubator with my startup company, and here's Flagship Ventures, which is the venture capital firm. We can meet regularly because we just walk down the street. Geography is very helpful. Okay? What has happened in Massachusetts is because of this huge number of small companies, the big ones move in. It's a very unusual model of economic development. They move in to partner with, look at, buy, whatever, steal the small companies. Okay? We now have 12 of the world's top 12 companies in Massachusetts precisely to do this. Many of them have moved their research. I asked when I was meeting with a group of Swiss, I said, why has Novartis moved almost all of their research out of Basel? Not just to Massachusetts, not just to Boston, but to exactly, where is it? This corner, this is Novartis. Why are they right here, and why are they building 3 buildings right here? Okay? You get the sense of why this is happening and the potential for economic growth. Okay? You want to see this replicated in many other places. And I would love to see this replicated in Tel Aviv. Okay? Well, okay. And, you know, I can go into what we do, what I do in the state. I mean, we basically, this is economic development money. I'll just go through it in 2 minutes. But basically, the Mass Life Sciences Center gives out $100 million a year in economic development funds to increase life sciences. And this report is public, and it shows that it works. Here's the scientific advisory board that I put together. And it's not really a scientific advisory board. What you'll notice on the left are a lot of scientists who work in academia. But what you don't know, none of you know the name David Walt, do you? He developed Illumina, the high-throughput DNA sequencing technology. Wow. Okay? Okay, Bob D'Amato at Children's Hospital. He developed lenalidomide. That's the another frontline treatment for multiple myeloma. Earned Children's Hospital almost $100 million in royalties. Okay? So we have absolutely top people on this advisory board. Where's Barbara Osborne? Here. I mean, you talk about a wild company. She generated a line of cloned cows that make human antibodies, transgenic cows, and sold it for many millions of dollars. It's a bunch of cows grazing in North Dakota. Okay, but they're making a lot of human antibodies that are useful for a whole variety of diseases. We have people who lead industry, who have developed or led large companies. Jose Carlos is the worldwide director of Pfizer Research. He sits on our board. We have 6 venture capital partners who evaluate companies. That's how we work. We have a lot of programs which I'll skip over. We give a lot of money to private institutions to help them develop unique centers for teaching or research. I'll just go into this one. Our most successful program is an internship, where undergraduates at any Massachusetts institution of higher education can work in a company for the summer. and the state pays the whole cost. It's had, it's now well over 200 students. It's to take students who have no idea, because most students have no idea what the biotech industry is like, and to work in a company to get the experience of working in a commercial operation. So you can see the kinds of things that a government can do. And I just have to end to this, because I'm in Israel. Okay, this shows me at the signing ceremony of the bill. And I'm showing you this for a reason, not just to sound arrogant. But, here I am. And these are people I've worked with in developing the Mass Life Sciences Center. Here is Governor Patrick. Here is the Lieutenant Governor Terry Murray. Number of senators and so forth in the background. This gentleman, Saul DeMacy, was the Speaker of the House of Representatives. He is now in the federal jail for corruption. So another, and probably my last lesson that I want to leave you with, is that be careful whom you associate with. Thank you very much. Okay, questions? Yes?
Do you know how many companies didn't success in the hospital?
Yes, I do.
Statistically, how much you have success?
About half fail. 2 of the companies I started have failed. That means nothing. That means absolutely nothing. Investor lose money, you go on to the next project. Okay? Failures are part of the game. Okay? Everyone understands that. It is a sign of honor that you started a company that failed. I am not joking. In many countries that I deal with, it is a sign of failure. We take risks in science and in developing companies. Failure is simply one of the options, and that's okay. My red cell company may fail, in which case all the time and effort I put into it I've lost. Big deal. If it works, if we get one product out of it, we'll be very successful.
You lose $1 billion.
That's not a lot of money these days. You have to take the risk. I'm glad you asked the question. This is a common attitude. But the investors understand it. They're very sophisticated. Flagship Ventures has made fortunes for their funds, as have Third Rock and Polaris and many of the others. It's part of the decision-making process. And don't worry about it. If you worry that everything is going to fail, you never get anywhere. Editas may fail, and the investors may lose several $100 million. But you know what will happen? Another company will spring up and do it better and get it to work. Okay? That's the philosophy. Come on.
So actually, we're going to move from here, those of
Wait a minute. You sure? You sure? Don't. I'm curious to hear from any of the students who have questions about actually. Yeah, here we go.
How much of the money is, do you have to bring your own money?
I bring nothing.
As a student that wants to go to the business.
Okay, you have to attract investors. None of us are rich enough to start a company. Okay? Just as an example, MIT has a competition where students get together and start companies and then try to get money from MIT. It's a 50K or 100K competition. And, the leading group, it's a practice in starting companies. But you have to learn how to make pitches to investors. And that's why it's very helpful. Students can't do it themselves. In other words, it'd be very unusual for a student to start a company. But if you get your thesis supervisor or a famous academic, that person will vouch for the technology.
So you only have to have the idea.
You need the idea, and you need to be able to formulate it in ways that I described to do it, yes. And you may need to have some experiments that say, yeah, what I'm thinking of is possible. And that's what I hope you've learned from this when you see how you take some of these discoveries out of the laboratory. You see, and say, okay, you know, what can I do with lentiviruses? That's HIV, for God's sakes. Although we don't talk about it. You're taking all the research that was done on HIV and converting it into gene therapy vectors. You'd never tell someone they're getting HIV. Okay? But, you know, it was that kind of idea. Can you use lentiviruses to do something? Or gene editing, or gene therapy, or whatever it is. You see. So you got to, you know, it takes, you can't do it yourself, but you'll need, you know, you need senior people, ideally who have done it before. Academics, students come to me all the time with ideas, and occasionally I even start a company with them. Okay? Anybody else? Yeah. A good what, I'm sorry?
Management.
Good. Yes, you need business people who know how to run companies. He's absolutely right. I mean, you can't, scientists generally are not equipped to run a company. You can be the chief scientific officer, but that's why you have venture capital people and professionals who run these companies. Exactly. With the new company, which is typical, we gave ourselves probably 3 years. 3 years and $10, $15 million. And we'll see. Either it's going to fold or it's going to take off. But it looks like it's taken off. I can't tell you what the developments are because they're confidential, but it looks like it's taken off. Okay? They're encouraged enough to keep putting more money into it. Good.
I'm happy that things are recorded and that hopefully you can move this to our university and especially the ones to help us get companies involved.
Look,
We have a patent company.
I know that, and that's why I'm standing here. And I've done this in many other countries that have equally strong university systems and not this culture of faculty entrepreneurs and business development. And you're not alone. There are many university cities in the United States that don't have this, and that they would love to. And it requires leadership at a lot of levels, including at the very top. So if I were to go further with this in Israel, I would insist on meeting with both the Minister of Education and the Minister of Health. Because it's at that level, if not the Prime Minister. What do you whatever you have. Whatever you have, I don't know your government. I just know you have whatever you have. But the point is, these are decisions that have to be taken at the top.
So, any other questions?
Okay.